Okay, so we are going to just talk a little bit about bonding and what it is and kind of what's going on there. So, if you guys remember back, we said that electrons were defined using our wave equation psi. And we said that anytime we have any electron, we can define it as this equation. And that dictates everything about the electron, including position, momentum, shape of the orbital. All that stuff is in this equation. Okay. So I'm just going to call this, we're just going to say psi. Okay. So that describes everything about the electron. Now, when atoms are bonding, this is still important. Okay. This psi is still important. And we're going to come back to that and kind of talk about that stuff later. But just a reminder, whenever we're talking about electrons, we always remember that it's defined as this kind of wave equation thingy. We're not going to ever write it out. We don't really care too much about it, but just know it's defined by an equation. So let's talk about an atom. Okay, so we got our little nucleus here. Okay. And the electron is defined by this equation. And so it's just going to be somewhere kind of in this general area. Okay. Just kind of flying all over the place. Somewhere in here. Okay. And I'm going to change colors real quick for that nucleus. So I'm going to put that nucleus in as blue instead of black. So there's my nucleus. So that is where my electron is. Now, if I have another atom, and we're going to do this as a red one, floating around over here. Let's put it right here. Okay. Its electron can be also defined as a new psi, a different wave equation, okay, because it's a different electron, and it's going to be found somewhere in this general area. Okay, so we're just going to put all these little dots showing where it could be. I put that dotted line just to kind of show kind of the extent of where it could be. Okay, there we go. Okay. So those two atoms right now have no interactions. Yes, these electrons will repel each other a little bit. Yes, this electron may be attracted to this nucleus a little bit. But bonding occurs when these two interactions cause these electron clouds to overlap. So as these nuclei get closer and closer together, then we start to have an interaction. Okay. And so what I'm going to do is I'm going to draw up this electron, and we're going to call it electron A. Okay. So if it's the blue, we're going to call this atom A, and we're going to call this atom B. Okay. So let's draw up my nuclei. I'm going to have my blue nuclei, and I'm going to have my red nuclei. Okay. And what's going to happen now is we're going to draw out my electron. And let's put my electron right here. Okay. Now, this electron is negatively charged. My nuclei are positively charged. So this electron is now going to get attracted to both of my nuclei. Okay. And it's going to want to start spending time in between these nuclei. And that is a bond. Okay. So a bond is when electrons start to become attracted to both nuclei. Okay. So that's what a chemical bond is. Now, A and B both have electrons. We're only going to be dealing with one electron in A and one electron in B. And what happens is, as they get closer and closer together, we get both of those electrons starting to be attracted. Okay. So let's draw my nuclei over here. One there, one there. Okay. And now, Let's do black for A, for my electron cloud for A, and then we'll do a different color for my electron cloud for B. What happens is now my electron is starting to get attracted over here to this red nuclei, to nuclei of B. So instead of spending all of their time just equally spaced around, we're going to see something kind of like this. Okay? It's going to spend time right here. And it's going to spend more time in between the two nuclei than it does outside of both nuclei. And the same thing happens with my electron from B. And actually, I'm going to do it as the exact same color, that black color. And it's going to actually look exactly the same. Kind of like that. And it's going to spend some time in here too. So now I got two electrons. And what happens is if we look at what we call our electron density, instead of being separated, now my electron density is actually in between my two nuclei. Okay? And there's actually two electrons there. Okay? That is the basics of chemical bonding. Now, there's a couple different types of chemical bonding. If we look at this, we say that the electron is equally attracted to both nuclei. But we could also have unequal attraction. The electron could be more attracted to the blue than it is to the red. Then what would happen is the electron density would shift towards the blue. So let's show that real quick. Okay. So again, here's the blue atom. Here's the red atom. Now, if they were equally attracted, we said that electron would spend most of the time straight in between. But if it's attracted more to the blue and less to the red, what we would actually see is it would spend more time over here and less time over here. Because so there would be my density. Okay, so if I put all my dots for where the electron can be found, we notice that there's a lot more spots that electron can be found over on the blue. Okay, and that is because the electrons are drawn in that direction. Okay, so the way we kind of depict it is we draw an arrow with a line through it. Okay, that's saying that it is being pulled in that direction. Okay? In physics, that is a way of showing what we call a vector. Don't need to worry too much about that. It's just being pulled over towards that. Why? Well, it's more attracted to the blue nuclei. Okay? And what dictates that? Well, that is electronegativity. Okay? So electronegativity dictates where that's going to shift. Now, could I get so much so that the electron gets completely pulled over to the blue? And yes, we can have that. Okay? And then if we have that, well, and this is both electrons, okay? All the electrons involved in the bonding. We're just going to say that it's just one right now. Or, well, sorry, two. We could also get it to where it is completely pulled over to the blue. So what this would look like then is the electrons are both going to spend all of their time over here. Okay. Now, since this had one electron and now it has two, technically its charge is 1 minus. Since this had one electron and now it has lost it, it is 1 plus. Are they going to be attracted to each other? Yeah, because negatives attracts positive. So this nuclei is going to be pulled towards that electron cloud. Okay? But the electrons are actually going to be spending pretty much all of their time around your blue atom and none of their time around the red atom. Okay? And that is what we call an ionic bond. Why is it ionic? Well, it's because one's negative and one's positive. Okay? And that all has to do with how attracted the electrons are to the atom, which is the electronegativity. So that is the basics of bonding. So if we go back and we kind of look at these, so let's look at our two types of, or our three types. This one is even time in between each. This one is slightly uneven, and this one is completely uneven. We have different names for those bonds. This one's ionic. This one over here is called covalent. And then this one right here is called polar covalent. Why is it called polar covalent? Well, it is covalent because the electrons are still spending time in the middle and around both things. They're just spending more time around one than the other. So it creates a pole. This side is slightly negative, and this side is slightly positive. That's why we use that little d. That means a partial negative and a partial positive. Okay, and so that's called a polar covalent bond. Now, what I want to talk about just for a couple minutes is what is actually going on with this bonding. Okay? And so we can kind of understand it. We'll go deeper in depth later. So we said that psi was how we described the electrons. Now we said we had we had our A and we had psi of our B. Okay, and atom A was our blue one. Okay, and the other one was our B was our red one. So those were the wave functions to describe those electrons on the red and the blue. When we bond, we actually mix our wave functions. Now, if you remember, we said that, let's get this back to black. The absolute value of psi squared, okay, was called our electron density. Okay. So our electron density was psi squared. And that told us where the electrons could be found. And for us, we said if we put a giant big old box, one-dimensional box, we just did a one-dimensional and we said, here's our giant box. What it's actually going to look like is we said, well, if it was the simplest, we would actually get something that would look kind of like that. Okay? Where the electron is more likely to be found right here than it is on the outside, where this is the center deal right here would be where your nucleus is. So the electron is going to be found most likely kind of closer to the nucleus than it is far away from the nucleus. Okay? And that was our psi squared. Okay? So if we have A and B, what we can actually do is we can look at psi A and psi B together. Okay? Now, there's different ways to combine them. Okay? So we said our original wave, if you guys remember, we said our original wave in the one-dimensional box just kind of looked like this, right? Okay. Now, it could also be below. Let's call this plus. And then if it were to repeat, bounce back, it would bounce back below the line. It could also be below the line, and we're going to call that negative. So there's two kind of ways it looks, a positive or a negative, because when this wave hits this, it's going to be going down. So then when it bounces back, it's going to bounce. I'm going to change the color. Because remember, we called them standing waves. It's going to bounce back kind of below the line. Then it's going to come up to here, bounce, and then go on the top of the line, and so on and so forth. So it's just kind of boom, it's going down, it's going up, and just back and forth and back and forth. So we have what we call a positive and a negative. So if we were to combine psi A and psi B, let's combine them. Well, we got a couple ways that we can combine them. We could combine the two positives together or the two negatives together. And we could also combine the positive of the A and the negative of the B. So what you're going to get is two different electron densities. You're going to get one where it's positive and negative and negative. Okay? And psi A and psi B combined is going to get us, let's just call this the new psi, and it's for our molecule, so let's just call it psi m, because this is our molecule wave function. Okay? So it can be combined where we combine, and then we square it. Well, you know what? Sorry, when we're combining it, it should be plus. We're adding them. Okay? So if we square this, we're going to get psi A plus psi B squared. Simple algebra, you're going to get psi A squared, okay, right, plus psi B squared, okay, and then we get the 2A plus B, 2 psi A, psi B. Now, these ones, psi A, psi B, that just looks like, let's just draw a little line. That just looks like this right over here. So psi A and psi B just look like this one right here. Now, A plus B, though, can be combined as positive and positive or positive and negative, because negative and negative make a positive, so we're totally good. It's the exact same thing. So we can either be plus and a plus or plus and a minus. You get two options on that. So this one right here, let's do the plus and the plus first. So if we had psi A, psi B getting combined, so let's draw this out. Now the box gets twice as big, right? So if we have psi A, here's this. So here is our nucleus of our B. Here's the nucleus of our A, right there. So we said psi A was positive. Why is that not working? Oh, come on. Don't do this to me now. There we go. So it could look like this. Here's the positive. Oops. Let's get that a little bit better. There's the positive, and that would be, that right there is psi A. And then psi B, oops, sorry, we're overlapping, would look like this. Psi B. Okay? So if I add those two things together, these right here, this is called your overlap. This is going to get bigger because you're adding two things that are both positive. So your resulting wave from the A and B, when they're both positive, will look like this. It's going to dip a little bit and then look like that. Okay? Where your nuclei are right here. So if we look at that, we see that the electron It broke again. The electron has quite a bit of chance to be found right in the middle and not a lot of chance to be found on the outsides. Perfect. Okay, this is bonding. Now, the other way I could combine psi A and psi B is by doing a positive and a negative. So we got psi A, let's have that a positive, and psi B, let's have that be a negative. Okay, so we're going to draw that exact same thing. Okay. So our red nuclei is over here. Our blue nuclei is over here. And now this time, though, this looks like this. Okay. Oops, sorry. Let's get our overlap. I want to undo that. I want to still have them overlapping by about the same amount. Okay. But this one, though, is going to be below because it's our negative. Looks like that. So that's A and B. So when I were to, if I were to combine them and then look at my electron density, what would actually happen? Oh, by this way, this would be psi squared. Sorry. This two right here, this is a negative value. This is a positive value. When I get those things together, what I'm actually going to get will look something where they cancel out. And this all here is negative. This all here is positive. So instead of them adding together to make it bigger, they're actually going to subtract from each other. And that is bad news bears. Because if those wave equations are subtracting, we get something that kind of looks like this. Okay? And a 0 here, and then a density over here. So if we look at that, are the electrons ever going to be found in between the two nuclei? No. And because of that, the nuclei are actually going to repel each other. That is called antibonding. Literally, it's the opposite of bonding. Whereas with the electrons in between, they can attract the nuclei and pull them together a little bit. Now, since the electrons aren't spending much time in between, you actually have two positive charges. And the positive charges are going to see each other, and that's going to cause repulsion and the actual the atoms to move away from each other, and that's antibonding. So when we are mixing our wave equations and looking at how electrons are going to behave, there are two ways to do it. One, where they constructively interfere and increase the chance of them to be found in between, which is bonding, and one where they destructively interfere, where you actually have no chance to be found in between, and that's called antibonding. So to review, there are three types of bonding that we worry about: covalent, polar covalent, where electrons want to spend time over here a little bit more, and ionic, where the electrons spend all their time around one, and then that negative and positive charge attracts the two nuclei together, the two atoms together. Then you also have mixing. Whenever we're dealing with two atoms, we have to deal with the wave equations for the electrons. Okay? And when you're dealing with wave equations, you have to add them together, and you get some weird things right here, boom, and that can either constructively interfere, increasing the likelihood of your electrons being found, or destructively, positive and a negative, and cause your electron density to be 0 in between. Okay? So that's what's going on, and we have bonding and antibonding. We will go more into this bonding and antibonding and molecular orbital theory later and what's going on there.